Welcome back to the AI podcast. I'm Alex, and today we're going to have a conversation that I think a lot of people in the industry need to hear right now. We are talking about AI agents, and specifically why most of them fail when they hit real production environments. My guest today is Daniel Okafor, CTO of Arcwise, formerly VP of AI platform at Shopify, where he helped build Kit, and before that, a senior research engineer at DeepMind. Daniel, welcome.
Thanks, Alex. Great to be here. This is a topic I feel very strongly about because I've been on both sides of it. I've built the research prototypes that look incredible in a demo, and I've also been the person who has to make them work when real users and real money are involved. Those are very different problems.
And that's exactly the tension I want to explore. Because right now, the hype around AI agents is at an all-time high. Every startup pitch deck has the word agent in it. Every major tech company is launching an agent framework. But when I talk to engineering leaders privately, a lot of them are telling me that their agent projects are struggling or stalled. What's going on?
What's going on is a fundamental mismatch between what people think agents are and what they actually need to be to work in production. Let me be direct about this. The vast majority of AI agent demos you see, the ones where an agent books a flight or writes code or manages your calendar, those demos work because they're operating in a controlled environment with a cherry-picked task and a human watching. The moment you remove any one of those conditions, the failure rate skyrockets.
Can you put a number on that? Like, what kind of failure rates are we actually talking about?
Sure. At Shopify, when we first deployed Kit as an autonomous agent for merchants, our initial success rate on complex multi-step tasks was about 62%. That means roughly 4 out of 10 times the agent either failed to complete the task, completed it incorrectly, or completed it in a way that the merchant didn't intend. And this was after months of development by a world-class engineering team.
62%. That's a number you'd never accept for a traditional software feature.
Exactly. If your checkout flow failed 38% of the time, you'd have 0 customers. But somehow the industry has convinced itself that those failure rates are acceptable for agents because, hey, it's AI, it's hard. And I think that mindset is genuinely dangerous because when an agent fails, the consequences can be worse than when a traditional feature fails. A bug in a checkout flow shows an error page. A bug in an autonomous agent might place the wrong ad campaign, send the wrong email to your entire customer list, or process a refund that shouldn't have been processed.
So the stakes are actually higher, not lower.
Much higher, and yet the reliability bar that teams are set at is much lower. That disconnect is the core of why most agent projects fail.
Before we go deeper into the failure modes, I want to make sure we're on the same page about definitions. What actually constitutes an AI agent? Because I feel like the term has become so overloaded that it's almost meaningless.
You're absolutely right, and that ambiguity is itself part of the problem. Here's my working definition. An AI agent is a system that takes a goal, decomposes it into steps, executes those steps autonomously, and adapts its approach based on the results it observes. The key word there is autonomously. If a human is approving every step, that's not really an agent. That's a copilot or an assistant or a workflow automation tool with an AI component. There's nothing wrong with those things, but they're fundamentally different from an agent.
So the defining characteristic is the degree of autonomy.
Right. And here's why that matters for production systems. The more autonomy you give a system, the more trust you need in that system. And trust in a system comes from predictability, reliability, and recoverability. Traditional software earns that trust through deterministic behavior. Given the same input, you get the same output. AI agents, by their nature, are non-deterministic. The same input can produce different reasoning chains, different actions, different outcomes. That's a fundamental challenge that no amount of prompt engineering solves.
That's a really important distinction. So you're saying that the very property that makes agents powerful, their ability to reason flexibly, is also the property that makes them unreliable.
Presley. And I think a lot of teams don't fully internalize this trade-off when they start building. They see the flexibility and creativity and they think this is amazing. It can handle anything. But handling anything means you can't predict what it will do. And in production systems, unpredictability is the enemy.
So what about agent frameworks? There's a whole ecosystem now. LangChain, Crew AI, AutoGPT, Microsoft's AutoGen. Are these helping or hurting?
I'm going to say something that might be controversial. I think most agent frameworks in their current form are actively setting teams up for failure. Here's why. These frameworks make it incredibly easy to build a demo. You can chain together a few LLM calls with some tool use and get something impressive running in an afternoon. But they abstract away low of the hard problems: error handling, state management, retry logic, observability, rollback mechanisms, resource limits, timeout handling. The framework gives you the happy path and leaves you to figure out everything else.
So they're optimizing for time to demo rather than time to production.
Exactly. And the gap between a working demo and a production system is enormous. At Arcwise, we've had companies come to us after spending 6 months building with an agent framework. They have a beautiful demo that works 85% of the time, and they need it to work 99.5% of the time. And closing that gap, going from 85 to 99.5, is harder than building the original 85%. That last 15% is where all the real engineering lives.
15% sounds small, but it's essentially an order of magnitude improvement in reliability.
It is, and most teams underestimate how much work it represents. At Shopify, getting Kit from our initial 62% success rate to 94% took us 18 months and a team of 12 engineers. That's 216 engineer months of work just to close that reliability gap. That's more effort than most startups have for their entire product.
Let's dig into the specific ways agents fail. You mentioned reliability. What are the most common failure patterns you see in production agent systems?
There are about 5 categories of failures that account for the vast majority of production agent issues. The first and most common is what I call cascading reasoning failures. This is when the agent makes a small mistake early in its reasoning chain, and that mistake compounds through every subsequent step. It's like the telephone game. By the time the agent finishes, the output bears almost no resemblance to what you actually wanted.
Can you give me a concrete example?
Sure, at Shopify, we had a scenario where a merchant asked Kit to create an ad campaign targeting customers who had purchased in the last 30 days with a budget of $500. Kit correctly identified the customer segment, but when it parsed the budget, it interpreted 500 as the daily budget instead of the total campaign budget. That single misinterpretation meant the agent set up a campaign that would spend $3,500 in a week instead of 500, and because the agent was autonomous, it actually launched the campaign. The merchant didn't notice until they got their billing statement.
That's the kind of failure that destroys trust permanently.
Completely. And here's what makes cascading failures so insidious. Each individual step in the agent's reasoning looked correct in isolation. It correctly identified the audience, correctly configured the ad creative, correctly set up the targeted parameters. The only thing it got wrong was the budget interpretation, and that error was subtle enough that even a human reviewer might have missed it if they were scanning quickly.
So the agent was 95% correct, but the 5% it got wrong was catastrophic.
Exactly, and this brings me to the second failure pattern, which is what I call boundary blindness. Agents don't inherently understand the boundaries of their authority. If you give an agent access to an API, it will use that API to accomplish its goal. It doesn't have an internal concept of, should I do this versus can I do this? A human employee knows that even though they have admin access to the billing system, they shouldn't change the pricing tier without getting approval. An agent with the same access will change it without hesitation if it thinks that's the best way to accomplish its goal.
That's a fascinating distinction. So the agent has capability without judgment.
Right, capability without judgment, and that gap is incredibly hard to close because it requires encoding organizational norms, business rules, and common sense into the agent's decision-making process. You can try to do this with system prompts and guardrails, but system prompts are fundamentally unreliable as a control mechanism for high-stakes decisions.
Why is that? A lot of teams rely heavily on system prompts as their primary guardrail.
Because system prompts are suggestions, not constraints. They're probabilistic, not deterministic. An LLM will follow a system prompt most of the time, but most of the time is not good enough when the failure case involves spending someone's money or deleting their data. I've seen agents ignore system prompt instructions under all sorts of conditions: long conversation contexts, adversarial inputs, edge cases that the prompt author didn't anticipate, even just random sampling variants. If your safety depends on a system prompt, your safety is a probability distribution, not a guarantee.
That's a really sobering statement. What are the other failure patterns?
The third one is state corruption. Agents that operate over multiple steps maintain some form of state. Their understanding of where they are in the task, what they've done, what they still need to do. and that state can get corrupted in subtle ways. The agent might lose track of a variable, double count a step, or merge information from two different tasks if it's handling multiple requests. At Shopify, we had a bug where Kit would occasionally cross-contaminate context between merchants. One merchant's product information would leak into another merchant's ad campaign. That was an absolute nightmare to debug because it only happened under specific concurrency conditions.
Do you eventually solve that?
We had to completely redesign our state management architecture. Instead of relying on the LLM's context window as the source of truth, we built an external state store with strict isolation guarantees. Every agent session gets its own immutable state object, and the LLM reads from and writes to that state through a structured API. It's more engineering work, but it eliminated an entire class of bugs.
So given all these failure modes, how do you actually design an agent system that can recover gracefully when things go wrong? Because it sounds like failure is inevitable. So the question becomes how you handle it.
That's exactly the right framing. At Arcwise, our core engineering philosophy is that every agent action will eventually fail, not might fail, will fail. And if you design from that assumption, you end up building very different systems than if you design from the optimistic assumption that the agent will usually get it right.
What does designing from that assumption look like architecturally?
There are 4 key patterns we use. The first is what I call checkpoint and rollback architecture. Every action the agent takes creates a checkpoint, and every checkpoint includes not just the state of the system, but the state of the world before the action was taken. So if an agent sends an email and the email was wrong, we can't unsend the email, but we can immediately send a correction or notify the responsible human. If an agent creates a database record, we can delete that record. If an agent calls an API, we log the exact request and response so we can undo the effect if needed.
So you're essentially building an undo system for AI.
Exactly. And it sounds obvious, but almost nobody does this. Most agent systems are fire and forget. The agent takes an action, moves to the next step, and there's no mechanism to reverse what just happened. At Arcwise, every action is wrapped in a transaction that can be compensated. We call them compensating transactions, which is actually a pattern borrowed from distributed systems architecture.
That's a really elegant application of proven distributed systems patterns to AI.
It is. And the second pattern is what we call progressive autonomy. Instead of building an agent that's fully autonomous from day one, you start with a system that requires human approval for every action. Then you gradually increase autonomy based on demonstrated reliability. We measure reliability per action type. If the agent has a 99% success rate on creating calendar events, it earns autonomy for that action. If it has a 92% success rate on sending customer emails, it still requires human approval for that action.
So autonomy is earned per capability, not granted globally.
Right. And this is a much more nuanced approach than the binary autonomous or not autonomous decision that most teams make. At Shopify, we eventually implemented something similar for Kit. We called it confidence gating. Every action Kit wanted to take came with a confidence score, and actions below a certain confidence threshold got routed to the merchant for approval. The threshold was different for different action types. Lower stakes actions like suggesting a social media post had a lower threshold than higher stakes actions like changing pricing.
That's smart because it means the agent can still operate at speed for the things it's good at while getting human oversight for the things it's still learning.
Exactly. The third pattern is structured output validation. One of the biggest sources of agent failures is that the agent produces an output that's technically valid, but semantically wrong. Like our budget example from earlier. The number was valid, it just meant the wrong thing. So we build validators for every action that check not just format, but semantic reasonability. Is this budget within the merchant's historical spending range? Is this email being sent to a number of recipients that makes sense? Is this API call modifying a resource that the agent should have access to?
So you're essentially building a second layer of intelligence that audits the first.
You could think of it that way. But the validators don't need to be intelligent. They're simple, rule-based checks. Is the budget between $10 and $10,000? Is the recipient count less than the merchant's subscriber list? These are cheap, deterministic checks that catch the most dangerous failures. You don't need another LLM to validate the first LLM. You need business rules encoded as code.
I love that distinction. Use AI where you need flexibility, use traditional code where you need guarantees.
That principle is at the core of everything we build. The fourth and final pattern is what I call fail loud and fast. Traditional software best practice says fail fast. For agents, I add fail loud. When an agent encounters something unexpected, it should not try to figure it out creatively. It should immediately stop, alert the responsible human, and provide a clear explanation of what happened and what it was trying to do. The worst possible behavior for an agent is to silently try to work around a problem, because that's how you get cascading failure.
Let's talk money. Because I think one of the biggest misconceptions about AI agents is that they're cheaper than having humans do the work. Is that actually true in your experience?
It is categorically not true for most use cases today, and I say that as someone whose company sells AI agent solutions. The economics of autonomous AI are much more complex than people realize. Let me break it down.
Please do.
First, there's the inference cost. Every time your agent reasons about something, that's an API call to a large language model. For a complex multi-step task, an agent might make 10 to 30 LLM calls. If you're using GPT-4 class models, which you need to for anything requiring real reasoning, each call costs somewhere between 1 and 10 cents depending on the context length. So a single agent task might cost anywhere from 10 cents to $3 in pure compute.
That doesn't sound that expensive.
Doesn't until you multiply it by volume. At Shopify, Kit was handling about 50,000 merchant requests per day at peak. At even 50 cents per request, that's $25,000 a day in inference costs alone. That's $9 million a year just to call the model. And that's before you factor in the engineering team building and maintaining the system, the infrastructure costs for running it, the monitoring and observability systems, and the cost of handling failure.
$9 million a year. That puts the cost conversation in a very different light.
It does. And here's the other thing people don't account for: the cost of agent failures. When an agent makes a mistake, someone has to fix it. That's human time. If your agent has a 5% failure rate and processes 50,000 requests a day, that's 2,500 failures per day that need human review and remediation. Even if each review takes 10 minutes, that's over 400 hours of human labor per day. You need 50 full-time employees just to handle the agent's mistakes.
So the agent isn't replacing humans. It's creating a different kind of human workload.
Exactly, and this is the dirty secret of the agent economy. Most agent deployments don't eliminate human labor, they transform it. Instead of humans doing the primary task, they're now monitoring the agent, reviewing edge cases, handling escalations, and fixing mistakes. In some cases, the total human effort is actually higher than it was before the agent, because the agent creates a new category of work that didn't exist before, which is agent supervision.
When does the economics actually work out in favor of agents then?
There are three conditions that make agents economically viable. First, the task must be high volume and relatively homogeneous. Agents get more cost-effective as the task volume increases because the fixed costs of building and maintaining the system get amortized over more tasks. Second, the consequences of failure must be bounded and reversible. If an agent mistake costs you $5 to fix, the economics can work. If a mistake costs you $50,000, you need near-perfect reliability. Third, and this is the one most people miss, the task must have a clear definition of done. Agents are much better at tasks where success is binary and measurable than at tasks where success is subjective or requires human judgment.
So the ideal agent use case is something like processing insurance claims or categorizing support tickets.
Exactly. High volume, clear success criteria, bounded downside. Those are the use cases where agents are genuinely transformative today. The use cases that VCs love to talk about, like autonomous research agents or AI chief of staff, those are much further from economic viability than the hype suggests.
That's a really pragmatic view. I appreciate you being honest about the limitations, even though your company is in this space.
Look, I think agents are going to be one of the most important technologies of the next decade. I genuinely believe that. But I also think the path to getting there involves a lot more honesty about where we are today than the industry is currently offering. Overselling agents hurts everyone, including companies like mine, because it sets unrealistic expectations that lead to disappointment and backlash.
So let's close with a forward look. Given everything we've discussed, what actually works today, and where do you think this is all headed?
What works today is narrow, well-scoped agent applications with strong guardrails and human oversight loops. Let me give you specific examples from what we're seeing at Arcwise. Our most successful deployment is an agent that handles accounts payable processing for a mid-sized logistics company. The agent receives invoices, extracts the relevant information, matches them against purchase orders, flags discrepancies, and queues approved invoices for payment. It handles about 12,000 invoices per month with a 97.3% accuracy rate.
Why does that particular use case work so well?
Several reasons. The input format is relatively constrained. Invoices follow predictable structures. The validation rules are clear and codified. Matching an invoice to a purchase order is a well-defined problem. And critically, the consequences of errors are bounded. If the agent misclassifies an invoice, a human reviewer catches it in the approval queue before any money moves. The agent saves the company about 60 hours of manual processing per month, and the error correction overhead is about 4 hours per month. That's a clear win.
So the agent is augmenting the human workflow rather than replacing it entirely.
And I think that's the key insight for what works today. The best production agents are not autonomous replacements for humans, they're force multipliers that handle the repetitive burden while humans retain oversight of the critical decision points.
What about the near future? What changes over the next 2 to 3 years?
I think 3 things will fundamentally change the agent landscape. First, models will get dramatically better at following constraints. We're already seeing this with structured output capabilities, function calling improvements, and better instruction adherence in newer models. As models become more reliable reasoners, the engineering burden of making agents production ready decreases.
So the foundation itself gets stronger.
Right. Second, I think we'll see the emergence of what I call agent middleware. Right now, every team building an agent has to solve the same hard infrastructure problems from scratch. State management, checkpoint and rollback, observability, progressive autonomy, failure handling. In 2 to 3 years, I think there will be mature platforms that handle all of this out of the box. The same way we don't build our own web servers anymore, we just use frameworks that handle the hard parts.
That would dramatically lower the barrier to building reliable agents.
Exactly. And third, and this is probably the most impactful, I think we'll develop much better evaluation and testing methodologies for agents. Right now, testing an agent is basically running it a bunch of times and seeing what happens. There's no equivalent of unit testing for agent behavior. But I'm seeing early work in formal verification for agent systems, adversarial testing frameworks, and simulation environments where you can stress test agents at scale before deploying them. When those tools mature, teams will be able to ship with much more confidence.
Daniel, this has been one of the most grounded and practical conversations about AI agents I've heard. Before we wrap, what's your one piece of advice for an engineering leader who's about to start an agent project?
Start with the failure mode, not the capabilities. Before you write a single line of agent code, sit down with your team and spend a full day brainstorming every way the agent could fail, every bad action it could take, every edge case that could lead to a harmful outcome. Build your architecture to handle those failure modes first, then add intelligence on top. If you build intelligence first and try to add reliability later, you'll spend 18 months learning the same lessons we did at Shopify.
Start with failures, not features. I love that. Daniel Okafor, CTO of Arcwise, thank you so much for joining us on the AI podcast.
Thanks, Alex. Enjoyed it.
And to our listeners, if you're building or evaluating AI agents, I hope this episode saves you some of the pain that Daniel's been through. Share it with your team before you kick off that agent project. We'll see you next week on the AI podcast.